All right, everybody, today's lab is all about finding the speed of sound in air. So I want to give you a little background. We know sound is a longitudinal wave, but we're going to model it here as a transverse wave. So when I hit the tuning fork, a series of compressions and expansions travel along this path. What we see here with the antinodes are going to be like the areas of high compression where you're going to hear a lot of sound, and the nodes where you won't hear any. Now this is a standing wave that I'm showing here, right? It will only go like this if the reflection back towards the source overlaps in such a way that you get this pattern, okay? So what I'm going to do is I'm going to take this tuning fork and I'm going to strike it, and then I'm going to raise this tube out of the water. And what that's going to do is it's going to change the distance between the opened end of the tube and the closed end. The closed end is this top surface, or the surface of the water, because that's where the sound will be reflected. So when I do that, you do that again. You might not have heard it that time, but you'll hear resonance when you get a standing wave in there. So at about that point, when I have the open end here and the closed end here, I've got resonance. And what I've found is the correct wavelength to match this frequency, because if you remember, at the closed end, you're going to have a node. And at the open end, you will have the antinode. So this is really what I'm capturing inside the tube itself. Okay, I'm not capturing all this stuff. I'm only capturing this quarter wavelength, right? Because an entire wavelength would go through a complete cycle. But here I'm only going through not even half a cycle. I've only got half of a half. Half of a half is a quarter of a wavelength. And that'll be the difference between the open end here and the closed end. Okay? And my daughter Taylor's going to help record some data here. And we're going to start with this particular wavelength. This frequency is 256 hertz. So we're going to set 256 there. Hold that, please. Okay. And then we're going to measure the difference between the top and the bottom. So the top position is at 65 centimeters. Whoops. Let me try that again. I want you guys to have good data, because you're going to be able to find the speed of sound in air here. Can I have that back, please? Thank you.
The difference between them.
So Taylor asked some really good questions. If you want to know what the difference between let's get this data first, and then we'll answer that question. So the top position is 0.65, and the bottom position is 0.32. Now when I get the next, let me make sure we're still recording. Sweet! Okay, when I get the next one, which is at 262 hertz, you might not be able to see it so well, but it's slightly different in size. So the length of this will change the frequency, and now I have a larger frequency of right here, 262. And let's see what we got for that fundamental frequency. The wavelength at the fundamental frequency. this isn't going to be perfect, guys, because usually you want to have more hands than this, but wow, we're about 64 and a half. And 33. And 0.33, I'm sorry. 0.645 and 0.33. Okay. Here's the next one. It's 349 hertz. And look how we're getting shorter still. This is the original, and this is the new one. You can hear the pitch, right? The pitch went up because the frequency went up. I'm trying really hard not to change that. All right, so the top dimension is 0.69. The bottom dimension, oops, that's 0.69. I'm sorry, that was 0.59. And the bottom dimension is 0.34. Thank you. All right, the next frequency, how much time do we have? Yay, we're still going. 384, this is a G note. You guys can imagine when we're doing this in class how frustrating it is. All right, so we're at 0.545 at the top and 0.35 at the bottom. With everybody hitting these and listening for the resonance, it can be quite a frustrating lab, but it's really a good lab. You get really good results. The next frequency is 440 hertz. This is an A note, by the way. Boy, I have a bad feeling I changed that. So 0.52 and 0.35.
Yeah.
That can't be right. Let's try that one more time, Taylor. Let me move this up here so I don't have to move around so much. There we go. Okay, I'm getting 0.51 and 0.36. Okay, there's some error built in here, guys, but I think we're going to be well within the range of 0.36. I don't know. We'll see. 494 is where we're at now. That's our next frequency. We've got two more, so we'll have to add another row. Well, you can hear that clear as a bell, can't you? I don't know that. Do that one more time. This is no special PVC. I just found it in the backyard, cut it, put it in this graduated cylinder. All right, 0.495, Taylor, and 0.36. Yeah, they're pretty close. And one last one, great, is 523. Now we're an entire octave above where we started. I think it's 0.485. and 0.355. Let's try that one more time just to verify we have time. Yep, still recording. Sweet, sweet, sweet. Now, of course, in your lab groups, let me do it one more time. In your lab groups, you'd have multiple hands doing this. You hold that. Thank you. Okay, I'm getting 0.495 and 0.36. Well, wait a minute, that was the same as the last one. So I'm a little confused. One of these is wrong. Do we have time to figure it out? We might. So let's look at 494. I'm sorry, guys. This is what happens, though. You look at your data, you see there's something you know you did wrong. You go back and you figure that out. My guess is Mr. Kuda just moved something. Yep, 0.51 and 0.355. Of course, that's the same as the last one. All right, I tell you what we're going to do is we're going to stop right here with what we have and plot this out. And I bet we get a, I'm guessing what we're going to do once we plot this out, even though you can see the imperfect methods that I was using, but I think you're going to find that it is within the realm of accepted values. Taylor's going to bring the camera close so you can get a better view of the data. All right, looking good. If you want to repeat this experiment at home, the procedures are there. You'll just need a set of tuning forks, or you can use the frequency generator from your phone, or just get a frequency generator app and do the same thing. All you need is a little piece of PVC, and even a bucket of water works just fine as long as you have some kind of meter stick. All right, guys.